All right, the topic for this video is going to be polygons and angles being found inside of them, or outside of them. We'll see here in a little bit. And our essential question is going to be, how are angle measures found in different polygons? So a little background information to get us started here. It says, after sufficiently investigating triangles, Euclid, the father of geometry, moved on to other polygons. He began by proving a few general theorems that could help him with any sort of polygon. Now, a couple different vocab words we need to know about polygons. A convex polygon is a closed figure formed by straight lines with all angles less than 180. A convex polygon is going to kind of be something like this. Now, all of our angles here are less than 180 degrees. They might be different, but we can say that they are all less than 180 degrees. There's nothing that opens up more than 180 degrees. No obtuse angles. As opposed to that, we have a concave polygon, which is a closed figure formed by straight lines with at least one angle greater than 180 degrees. So that could look something like this, right? If we look at this angle right there, it is more than 180 degrees, which creates this kind of cave-looking area. It bends inward on itself. That's how I remember concave. Concave polygons tend to kind of break some of these rules that we're going to be looking at later on. We're going to be mainly focusing on convex polygons. And then one last term here, we've got a regular polygon. A regular polygon is an equiangular and equilateral polygon, meaning that it has all angles that are equal and all sides that are equal. So all 6 sides on this polygon that I just drew are congruent, and all 6 angles are going to be congruent. Equiangular refers to the angles. Equilateral refers to the sides. Oops, didn't want to do yellow there. Okay. So we'll see some rules in this video that have to do with the equilateral or the regular polygons as well. All right, to get us started here, we got example 1 that's going to kind of get the ball rolling for one of our first theorems that Euclid found out. It says, example 1, pick a vertex and draw all possible diagonals from that point. Use the triangle sum theorem to determine the sum of all the interior angles. Okay, so for this first one, if we pick a vertex on our triangle here, and we try to draw all possible diagonals from that point, it's not going to really work because you can't draw a diagonal on a triangle because there's not another vertex that you can draw a line to other than the other 2 vertexes. So it's kind of redundant for this one. We know that the sum of the interior angles of a triangle is just 180 degrees. So we don't have to do anything for that one. But if we pick a vertex on our quadrilateral here, we can draw one diagonal here, right, to this other side. And by doing that, we end up forming 2 separate triangles. And we know that each triangle has 180 degrees inside of it. So 180 times 2 for our 2 triangles is 360 degrees. It tells us that there's 360 degrees inside every single quadrilateral. Right, 1 triangle gives us 180 degrees for the first. 2 triangles gives us 180 times 2 for the quadrilateral. And then moving on to the pentagon, if we do the same thing here, I could actually draw a diagonal going this way. And I could draw another diagonal to this other vertex. So by doing that, it creates 3 triangles, each triangle having 180 degrees, which would give us a sum of 540. So what is that going to tell us here? We can kind of follow this pattern to figure out how many degrees there are going to be in any sort of polygon. Because as you can see, as we increase the number of sides of the polygon, like we started with a 3-sided shape, then we went to a 4-sided shape, then we went to a 5-sided shape. Each time we increase the number of sides, if we add one side, we add 180 degrees. So that pattern is what's going to give rise to what we call the interior angle sum theorem. Here's what it says. It says if a convex polygon has n sides, where n just represents the number of sides, so we could have a 10-sided shape and n would be 10, then the sum of the interior angles can be found by the equation n minus 2 times 180. And I'll just say that s equals n minus 2 times 180, where s is the sum. So what is this even referring to? Well, this n minus 2 business right there, that is the number of triangles that can be formed inside of our shape. Like take, for example, the pentagon that we did that had the sum of 540. Well, there's 5 sides, so my n would be 5. 5 minus 2 is 3, which represents there's 3 triangles in there. So 3 times 180 gives us the 540. All right, so that is our interior angle sum theorem. N minus 2 times 180. And let's give that a shot on the inside of your notes here. So top left on the inside, example 2 says, find the interior angle sum for the following convex polygons. So first up is a hexagon. Now a hexagon has 6 sides. So we will do 6 minus 2 times 180. 6 minus 2 is 4 times 180. And 4 times 180 gives us 720 degrees. Now remember that 4 means that if we drew out the hexagon, we would see that we could make 4 triangles in there. A decagon has 10 sides. So we'll do 10 minus 2 times 180, which is 8 times 180. And 8 times 180 is 1440. So inside every single decagon is 1,440 degrees. Nonagon has 9 sides. So my n is 9, so I'll do an n 9 minus 2 times 180, which would be 7 times 180. 7 times 180 is going to give me 1,260 degrees inside any nonagon. And then a 22gon, that's obviously 22 sides. So we're going to do 22 minus 2 times 180, which means that we could make 20 different triangles inside a 22gon. And that's going to give me 3,960 degrees inside any one of those. So this interior angle sum theorem can be used to find out how many degrees there are going to be inside any polygon. Doesn't matter how you're going to kind of draw that thing. As long as it's convex, then that's how we'll find it. Okay, so how can we use this thing? Well, let's look at example 3 here. It says solve for x. And we can see that we've got this shape here. There's 1, 2, 3, 4, 5, 6 sides on this thing, right? So this is a hexagon. And as we saw just above, if we do 6 minus 2 times 180, that's going to give us 720 degrees. So that tells me that inside this hexagon, all 6 of those interior angles have to add up to be 720. So if I add up all those angles, I should be able to set it equal to 720. And that's exactly what I'm going to do. Starting with angle A, I guess. Angle A is x, plus angle B is 2x, plus angle C is x plus 10, plus angle D is 124, plus angle E is 2x, plus angle F is 2x plus 10. If I add up all of those, it should be equal to 720. Now if I combine some like terms, x, 2x, x, 2x, 2x, adding all those together, I get 8x. And then adding the 10 and the 124 and the 10, that should be 144 equals 720. If I subtract the 144, 720 minus 144 is 576. And then I will divide that. 576 divided by 8 is 72. So x has to be 72. We can try this kind of strategy here one more time with example 4 here. If I count up the number of sides on this thing, I got 1, 2, 3, 4, 5. This is a pentagon. So I'm going to do 5 minus 2 times 180 to figure out how many degrees there are inside of that thing. We saw the pentagon on the front. We know that that should be 540 now. So there's 540 degrees inside any sort of pentagon. So let's add up all the angles. A is 70, B is x plus 40, C is x plus 60, plus another 60 for D, plus x plus 10 for E. I know that's got to be equal to 540. Got an x, an x, an x. That's 3 x's. For my constants here, I've got 70 and 40 and 60 and 60 and 10. If I add up all of those, what am I going to get? 170, 230, 240 for all the constants. That's equal to 540. If I subtract the 240 after that, I'm going to get 300. So 3x equals 300. And dividing is going to give me 100. So x is 100 in this one. So we can see the interior angle sum theorem helps us out with polygons that are not triangles. Obviously, we know by now that triangles have to sum up to 180 for their interior angles, but other polygons don't follow that rule. And if you ever don't know it off the top of your head, interior angle sum theorem will let you find out what all those angles have to add up to be. Now, our next rule is going to be a variation on the one that we just saw. So if we want to find one single interior angle from a regular polygon, remember regular polygons where all the sides and angles are the same, then we can use this theorem. It says if a regular polygon has n sides, then the measure of one interior angle can be found by the equation. And we will say that the angle is equal to n minus 2 times 180 divided by n. Okay, so you can tell that we start off with that n minus 2 times 180 on the top part. That finds the sum of all of them. And then you divide by how many there are, which is n, right? A polygon with n sides also has n angles. So, if we wanted to find one interior angle of a hexagon, we would do 6 minus 2 times 180 all over 6. And that's how we'll find one single angle. So let's just try that out a few times here. With example 5, it says find the measure of one interior angle of the following regular polygons. A heptagon has 7 sides. So we would do 7 minus 2 times 180 divided by 7. So 7 minus 2 times 180 all over 7. It's going to give me 128 And I'll round to the nearest tenth of 0.6 degrees. So a regular heptagon has 7 angles, all being 128.6 degrees. An octagon obviously has 8 sides. So we would do 8 minus 2 times 180 divided by 8. And if we do that, I'm getting 135 degrees. So an octagon has 8 sides, or a regular octagon would have 8 angles, each one being 135. Quadrilateral obviously has 4 sides. So we would do 4 minus 2 times 180 divided by 4. And we should get 90 for that one. A regular quadrilateral is just a fancy way of saying a square. So, of course, a square has 90-degree angles. A dodecagon has 12 sides. So we would do 12 minus 2 times 180 divided by 12. And for those dodecagons, we should get 150 degrees. So each angle in a regular dodecagon is 150 degrees. Now, once again, of course, that rule can only be used for regular polygons. As we saw above on these ones, these were definitely irregular polygons because all the angles were different. I mean, some of them might have been the same, but they certainly weren't all the same. So those were irregular. This rule here can only be used for regular polygons. All right, so those were some rules for the interiors. Now let's talk about the exterior angle sum theorem. So if a convex polygon has insides, I guess before, these are what exterior angles look like, right? They're being formed on the outside. We saw it in a previous video when we were talking about the exterior angles on triangles, but this is what exterior angles look like on other polygons. So back to this. It says if a convex polygon has insides, then the sum of the interior angles, oops, that should be exterior. Your version will have that fixed. And the sum of the exterior angles can be found by the equation of S for sum equals 360. It's kind of strange, but the exterior angles of any polygon will always sum up to be 360. There is no formula. It's just always 360. So if you ever see a problem like this that says find the exterior angle sum for the following convex polygons, a triangle, the exterior angles of a triangle, all 3 of them, add up to be 360. A pentagon, 5 sides. Still 360. 5 angles that add up to be 360. A 13-gon, 13 sides, 13 exterior angles, 360 degrees. Hexagon, 6 sides. Guess what? The sum of them still add up to be 360. All right, it seems like it's a trick. It's not a trick. If we look at example 7 here, we've got a pentagon, right? We've got 1, 2, 3, 4, 5 sides, but guess what? Doesn't matter. All 5 of those exterior angles have to add up to be 360. So I will do 2x plus 2x plus 45 plus 2x plus 2x minus 5 all equals 360. So that is 2x, 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 2x. That is 8 x's. Plus a 45 minus 5 is 40. Is equal to 360. So combine my like terms. If I subtract the 40 here, I'm going to get 8x is equal to 320. And that should give me, if I do 320 divided by 8, I get 40. So that type of equation that we just set up there, the exterior angles always have to add up to be 360. Like when we were doing these ones with the interior angles, we had to do the interior angle sum theorem to figure out what to set the equation equal to. Because the interior angles vary as to how much they're going to add up to be. The exterior angles remain constant. They will always add up to be 360. Going on here, if we want to find one single exterior angle of a regular polygon, remember regular means that they're all the same, then we can do the formula of angle is equal to 360 divided by n. Think of this as the counterpart to this formula that we looked at. Remember how on that one we took the sum of the interior angles divided by the number of interior angles. That's how we found one of them on a regular polygon. Same idea here. On this one we do the sum of the exterior angles, which is 360, divided by the number of exterior angles, which is n. So pretty easy formula here. Let's give it a shot. For the 11gon, we will just do 11, nope. I'm sorry, already messed it up. We will do 360, which is the sum divided by 11. And that's not going to be a nice number, but let me see what I get. We'll round to the nearest tenth. 32.7. 32.7 degrees. So 11 angles of 32.7 would sum up to be 360. For a decagon is, of course, 10 sides. So we would do 360 divided by 10, and we would get 36 degrees. So 10 36-degree angles would give us the sum of 360. For a nonagon, 9 sides, so we would do 360 divided by 9, which would give us 40. So 9 exterior angles, each being 40 degrees for a regular nonagon. That would sum up to be that 360. And a heptagon, that's the one people always forget. Heptagon is 7 sides. We would do 360 divided by 7. And we would find out that there are 7 51.4 degree angles, adding up to be that sum of 360. Okay, so your turn to try a few things on the your turn page here. For example, when you got this big table, okay, notice that for each row, I've given you one piece of information. Maybe it's the number of sides, maybe it's the interior angle sum, and I want you to figure out the rest of the information from there. You might need to think a little bit backwards. Just do your best, try to figure it out. The bottom two there are going to be two of those kind of algebraic ones where you're going to be solving for x. So see what you can do for the table. If you get stuck, refer back to the rules up here, right? N means the number of sides. Then you've got your interior angle sum theorem here. You've got all 4 rules up there. Those are at the top. Do your best to, like I said, you might need to work backwards on a few of these, but see if you can figure it out. The ones where I gave you the number of sides, those ones should be easy, like the 3 and the 7. The other ones you might need to do a little brainstorming as to figure out how you can reverse engineer some of this stuff. But the bottom ones, you've got examples just like that up above. So give that a shot and then come back and continue the video when you are ready to check. Okay, hopefully that went well. So number of sides is 3. That means the interior angle sum you should have found by doing 3 minus 2 times 180, which is 180. For one interior angle of a regular polygon, that would have been 3 minus 2 times 180 divided by 3, which should have given you 60. The exterior angle sum is always 360. In fact, I mean, we can just go ahead and put this down for everything, right? That's never going to change. And then one exterior angle of a regular polygon, it should have been 120 by doing 360 divided by 3. Now, here's where it gets a little bit tricky. For the next one, I gave you the interior angle sum, and I said it was 1080. Now, to kind of go backwards from there, I think the best way of thinking about it is undoing this rule, right? To do the interior angle sum theorem, you take the number of sides, you subtract 2, and then you multiply by 180. If I start undoing that, then the first thing I should do is divide by 180. if you do 1080 divided by 180, you get 6. And then you add 2 to it instead of subtracting 2 like you do the normal interior angle sum theorem. And you would get 6 plus 2 is 8. And that tells you how many sides you have. Your n is now 8. If you want to check that, just do 8 minus 2 times 180. That's 6 times 180, which gives us 1080, right? All right, so we figured out the number of sides. Number of sides is 8. Now we just have to do our normal stuff. 8 minus 2 times 180 divided by 8, which is just 1080 divided by 8, which is 135. So this is an octagon. And then if we do 360 divided by 8, we're going to get 45. All right. So now for the next one, I gave you one exterior angle of a regular polygon. Now, if we kind of think about going backwards on this one as well, if we know that one single exterior angle is 30, and we know that the sum of them has to be 360, then we could do 360 divided by 30, and we would figure out that that is 12. So that tells me there's 12 exterior angles, which means that my n is 12. And now that I figured out my n, I can do all my normal stuff. All right, 12 minus 2 times 180. That's going to give me 1800. And then if I do 12 minus 2 times 180 divided by 12, that is going to be 150. All right, now this next one I think is probably the trickiest one. I gave you the one single interior angle from the regular polygon. Now, maybe some of you guys picked up on this by doing the table, but notice this and this. The regular interior angle, the regular exterior angle. Regular interior angle, regular exterior angle, regular interior, regular exterior. You notice anything about those numbers? 60 and 120, 135 and 45, 150 and 30. It's a linear pair. They're always supplementary. The interior and the exterior obviously would combine to form a straight line, right? They always have to add up to 180. So if I do just 180 minus 108, I get 72. So the exterior angle has to be 72. Now, why would I do that? Because of what we just did up above. I think that that's the easiest way to find out what n is. If we know that one single exterior angle is 72, 360 divided by 72 will give me 5. So n is 5. Oops, I wanted to do that in red. And now that we know what our n is, now we can do 5 minus 2 times 180. This is a pentagon. We've seen this multiple times. This is 540 degrees. So, cool fact that the interior angle and the exterior angle always have to add up to 180. Some of that, that might have been obvious to some of you. This last one, though, this one's straightforward. They gave us n. So we just do 7 minus 2 times 180. This is a heptagon. Heptagons should always have 900 degrees inside of them. We do 7 minus 2 times 180 divided by 7. And we get 128.6. And then we can do 360 divided by 7. And we get 51.4, which is supplementary with our 128.6. Okay, last two here. We got a little interior angle one. Got a little exterior angle here. This is a pentagon, so we do 5 minus 2 times 180 to find out that all of that's got to add up to be 540. So I will do x minus 10 plus x plus 2x minus 40 plus 60 plus x plus 30 is equal to 540. How many x's I got there? 1, 2, 3, 4, 5 x's. Then I've got minus 10, minus 40, that's minus 50, plus 60 is plus 10, plus 30 is 40. So 5x plus 40 equals 540. Oh, this is looking quite nice. We subtract the 40, we get 5x equals 500. So x is 100. Cool. And then the last one, those are all exterior angles. We know that exterior angles have to add up to be 360. So I'm going to do 105 plus 2x plus 5 plus 65 plus x plus 5 plus 4x plus 2x equals 360. 2x's, 3x, 7x, 11x, I believe. Let me make sure I added that up right. 2, 3, 7, 9. Wait. 2x plus x is 3x. Oh, yeah, that's just 9x. I don't know where I got 11x. So 9x, and then what's going on with our constants? 105 plus 5 is 110. 175. 180. 9x plus 180 equals 360. We subtract the 180, we get 9x is equal to 180, and that's going to give me 20. All right, hopefully that went well for y'all, and that's going to wrap up this video.